Hello, in this lecture we'll find out the area of the green semicircle using two different methods. In the drawing we have two semicircles. This is the white semicircle, this is the green semicircle. In addition, you know that this is line segment AC, that is equals to 5 units in its length. This is line segment CB, that is equals to 1 unit in its length. Again, our mission is to find out the area of this green semicircle. So we start with the first method, and we join points P and B together by a straight line. In the next step, I'll copy the white semicircle in a new page and we'll implement rule 7 on the white semicircle. This is the white semicircle that I copied from the original drawing. AB is the diameter of this white semicircle, so I write it down. Actually, by joining points P and B together by a straight line, we created here peripheral angle APB. This is peripheral angle APB, and it is subtended on AB, that is the diameter of this semicircle, and therefore we can implement here rule 7. I repeat quickly on rule 7. According to rule 7, if a peripheral angle subtends on the diameter of the circle, then it is equal to 90 degrees in its size. So in the drawing we have a circle, and AB is the diameter of the circle, and we have here also peripheral angle ACB. This is peripheral angle ACB that is subtended on AB, that is the diameter of the circle. Therefore this peripheral angle ACB equals to 90 degrees in its size. So we can actually implement rule 7 in our drawing. Why? Because in our drawing we have peripheral angle APB that is subtended on AB, that is the diameter of this white semicircle. Therefore, according to rule 7, this peripheral angle APB must be equal to 90 degrees in its size. Okay. So angle APB equals to 90 degrees in its size. In the next step, we will join points P and C together by a straight line. And I'll copy the green semicircle and we'll implement all 7 on the green semicircle. So this is the green semicircle that I copied from the original drawing. It is very easy to see that AP is the diameter of the green semicircle. So I write it down. AP is the diameter of this green semicircle. And here we have triangle ACP that is subtended on AP, that is the diameter of the green semicircle, and therefore according to rule 7, triangle ACP equals to 90 degrees in its size. This is triangle ACP, and according to rule 7, it is equal to 90 degrees in its size. Because it is subtended on AP, that is the diameter of this green semicircle. So, if you focus on the original drawing, you can see that this is angle A, and angle A is a common angle that belongs to both right angles. It belongs to the right angle APC, and angle A also belongs to the right angle APB. So angle A is a common angle that belongs to both angles. So we define the size of this angle A as alpha. So yeah, this is angle A, and it is equals to alpha according to our definition. And we will focus on the green right angle APC. In the green right angle APC, this angle equals to alpha, this angle equals to 90 degrees. Therefore, this third missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees is equals to 180 degrees. That is the sum of the angles in any triangle. Likewise, in the right angle APB, angle A is a common angle that belongs to both triangles, and according to our definition, this angle A equals to alpha. So in the right angle APB, this angle equals to alpha, this angle equals to 90 degrees. Therefore, this third missing angle must be equal to 90 degrees minus alpha. In the next step, we'll copy this right triangle APB and this green triangle APC in the new page, and we'll prove that those two right angles are similar to each other according to angle similarity rule. So actually, this is the green right angle APC that are going from the original drawing, and this is the right angle APB that I also copied from the original drawing. In the next step, we prove that those two right angles are similar to each other according to angle similarity rule. So I write it down. We'll prove that the right angle APB is similar to this green right angle APC. So why those two right angles are similar to each other? First of all, those two angles, they are both equal to 90 degrees, and therefore they are equal to each other. So this is angle APB in the right angle APB. And it is equal to this angle. This is actually angle ACP in the right triangle APC. Repeat again. Angle APB in the right triangle APB equals to angle ACP in the right triangle APC. They are both equal to alpha, therefore they are equal to each other. In addition, this is angle alpha. Angle alpha is a common angle that belongs to both triangles. So we can write down that angle alpha is equals to itself as a common angle that belongs to both triangles. So if we relate to angle alpha as it belongs to the right angle, it will be defined as angle PAB, and it equals to itself. So if we relate to angle alpha as it belongs to the green triangle, it will be defined as angle PAC. Repeat again. This equation means that angle alpha equals to itself. We just called to angle alpha two different names. Angle alpha equals to itself as a common angle that belongs to both triangles. And finally, those two angles, they are both equal to 90 degrees minus alpha, therefore they are equal to each other. So actually this is angle PBA in the right triangle APB, and it is equal to this angle. This is actually angle APC in the green triangle PCA. Repeat again. Angle PBA in the right triangle equals to angle APC in the green triangle. They are both equal to 90 degrees minus alpha, therefore they are equal to each other. So actually proved that all the fingers of this right green triangle APC are correspondingly equal to all the fingers of this right triangle APB, and therefore actually proved that those two right triangles are similar to each other according to angle similarity rule. So I write it down. So actually proved that the right triangle APB is similar. This is the sign of similar to the right green triangle APC, according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We derive that side AB in the right triangle APB over side AP in the green triangle APC equals to side AP in the right triangle APB over side AC in the green triangle APC. Repeat again. We derive that side AB in the right triangle over side AP in the green triangle equals to side AP in the right triangle over side AC in the green triangle. What is the length of AB? From the original drawing, it is very easy to see that in total AB equals to 5 plus 1, that is 6. So it is 6 over AP. AP is the missing side, so we leave it as it is. Over AP equals to is equals to AP over AC. AC is 5. So to that we should find out that 6 over AP equals to AP over 5. Here we cross multiply this equation and you get that 5 times 6 is 30. So 30 equals to AP times AP is AP squared. 30 equals to AP squared. We take a root out of this equation and finally get that the missing side AP equals to the square root of 30 units in its length. AP is the diameter of this green semicircle and it equals to the square root of 30 units in its length. If the diameter of the green semicircle AP equals to the square root of 30, it means that the radius must be equal to half of it. So the radius R, we define the radius of this green semicircle as R. The radius R must be equal to the diameter AP over 2. The diameter AP is equal to 30, and square root of 30 over 2 equals to the radius R of the green semicircle. So the radius R in total of the green semicircle equals to the square root of 30 over 2 units. Repeat again, the radius R of this green semicircle equals to square root of 30 over 2 units. Again, our mission is to find out the area of this green semicircle. So the area of this green semicircle equals to pi r squared over 2. So write it down. The area of this green semicircle is equals to pi r squared over 2. So it is pi, r is equal to 30 over 2, therefore r squared is equal to 30 over 2 squared divided by 2. So the area of the green semicircle equals to pi here we have square root of 30 square is 30 over 2 square is over 4 divided by 2. So the area of the green semicircle in total equals to pi, and we have 30 over 4 over 2 equals to 30 over 4 times 2. Here we have 30 over 2 is 15, so in total this expression equals to 15 pi over 4. 15 over 4 is 3.75, so in total this expression equals to 3.75 pi. 3.75 pi equals to 11.78 square units. So in conclusion, we can find out that the area of the green semicircle of this green semicircle equals to either 3.75 pi square units, so in terms of numbers it equals to 11.78 square units. So finish with the first method. In the next step, I will present to you how to find out the area of this green semicircle according to the second method. In the second method, we join points P and B together by a straight line. And I'll copy the white semicircle in a new page, and again we'll implement rule 7 on the white semicircle exactly as we did in the first method. So actually this is the white semicircle that according to the original drawing. We know that AB is the diameter of the white semicircle, so I'll write it down. AB is the diameter of this white semicircle. By joining points P and B together by a straight line, we create the peripheral angle APB. This is peripheral angle APB, and it is subtended on AB, that is the diameter of this white semicircle. And therefore, according to rule 7, peripheral angle APB must be equal to 90 degrees in its size. So this angle, peripheral angle APB equals to 90 degrees in its size, according to rule 7. What is the meaning that peripheral angle APB equals to 90 degrees in its size? It means that line segment BP is perpendicular to line segment PA. Again, line segment BP is perpendicular to PA. So here, line segment BP is perpendicular to PA. And PA is the diameter of the green semicircle. And we will find out the center of this green semicircle. So here, the center of this green semicircle is here. This is the center of this semicircle. And we define the center of this green semicircle as point O. So point O is the center, by the way, the center of this green semicircle must be located on the diameter AP. So point O is located on the diameter AP of the green semicircle. So point O is the center of the green semicircle, point P is the point on the green semicircle itself, therefore OP is the radius of this green semicircle, so we define the radius of this green semicircle as R, therefore OP equals to R. So, and I'll copy point O to the new domain here. So okay, this is point O that is coming from the original domain, and OP is the radius of this green semicircle that equals to R. in conclusion, we should found out that line segment BP is perpendicular to the radius PR of the green semicircle. Okay, line segment BP is perpendicular to the radius PO of this green semicircle. And whenever you have a line segment that is perpendicular to a radius, you can implement rule 1. I'll repeat quickly on rule 1. According to rule 1, a tangent to the circle is perpendicular to the radius drawn to its point of tendency. We have here OM is the radius of this circle that is equal to R, and here line segment AB is perpendicular to the radius MO. Again, line segment AB is perpendicular to the radius MO. Here line segment AB is perpendicular to the radius MO. And because of the fact that line segment AB is perpendicular to MO, line segment AB is defined as a tangent to this circle. So we can implement rule 1 in our drawing. Why? Because in our drawing we have line segment BP is perpendicular to the radius PO of the green semicircle, and therefore according to rule 1, line segment BP must be defined as a tangent to the green semicircle. So I write it down. This is line segment BP, and because of the fact that it is perpendicular to the radius PO of the green semicircle, line segment PB is defined as a tangent to the green semicircle. Again, line segment PB is defined as a tangent to the green semicircle. So, and we have here also from the common example point B, we have tangent BP to this green semicircle, and for the same common example point B, we have also this chord AC of the green semicircle. Okay, so here we can implement rule 10. I'll repeat quickly on rule 10. First of all, BP, line segment BP is tangent to this to the radius PO, so this angle equals to 90 degrees in its size. Again, line segment BP is tangent to the green semicircle at point P. In addition, from the common example point B, we have here tangent chord AC. Therefore, we can implement here rule 10. Repeat quickly on rule 10. According to rule 10, rule 10 is true in any circle. So, in any circle, if AB is a chord, you can see here that AB is a chord of this circle, and PT is tangent to the circle. Here, from the common example point P, we have tangent PT that is tangent to this circle at point T. So, in this drawing, the following equation is true, that PT square equals to PA times PB. Again, PT square equals to PA times PB. We can actually implement this rule 10 in our drawing. Why? Because in our drawing, if we focus on this common example point B, from this common example point B, we have tangent BP to the green semicircle. And in addition, we have also here chord AC that exists from the same common example point B. So all the requirements of rule 10 are satisfied, and therefore we can implement here rule 10. According to rule 10, PB square equals to BC times BA. Again, PB square, BP square equals to PB square equals to BC times BA. So I write it down. According to rule 10, PB square equals to BC times BA. Okay, again, according to rule 10, PB square equals to BC times BA. Okay. PB is the missing tangent, so we leave it as it is. So PB square equals to BC. BC is 1, so we substitute BC by 1 times BA. BA in total equals to 5 plus 1, that is 6. So in conclusion, according to rule 10, we actually found out that PB square equals to 1 times 6, that is 6. So PB square equals to 6. We take out of this equation, and finally we get that the missing tangent PB equals to the square root of 6 units in its length. So here PB equals to the square root of 6 units in its length. In the next step, I'll copy the right triangle APB in a new page, and we'll implement the Pythagoras theorem on this right triangle APB. Actually, we already found out, we know that the hypotenuse AB equals to 6. We already found out that side PB equals to the square root of 6 units in itself. Side PB equals to the square root of 6 units in its length. And the only missing side on this right triangle APB is side AP. So by implementing the Pythagoras theorem on this right triangle APB, we'll find out the missing side AP. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So actually, this is the right triangle APB that I copied from the original drawing. According to the Pythagoras theorem, in this right triangle APB, AB square equals to AP square plus PB square. And again, AB square equals to AP square plus PB square. So I write it down. AB square, that is the square of the hypotenuse, equals to AP square plus PB square. AB is 6, therefore AB square is 6 squared, that is 36. And it is equal to AP square. AP is the missing side, so we leave it as it is. Plus PB square. PB equals to the square root of 6, therefore PB square equals to the square root of 6 units. PB equals to the square root of 6 square. That is, square root of 6 square is 6. So we found out that 36 equals to AP square plus 6. We subtract 6 from this equation. And finally we get that AP square equals to 36 minus 6 is 30. We take the root out of this equation and we get that the missing side AP equals to the square root of 30 units in its length. So if I found out that AP, that is the hypotenuse of the green semicircle, equals to the square root of 30 units in its length. If the hypotenuse AP equals to the square root of 30, it means that the radius of this green semicircle must be equal to AP over 2. So R equals to AP over 2. AP is equal to 30. So the radius of this green semicircle equals to the square root of 30 over 2. Again, our mission is to find out the area of this green semicircle. And the area of the green semicircle is of course equals to pi r squared over 2. But again, the area of the green semicircle equals to pi r squared over 2. So it is pi r is equal to 30 over 2, therefore r squared is equal to 30 over 2 squared divided by 2. So it is pi, and square root of 30 square is 30, over 2 square is 4 divided by 2. So there of the green semicircle in total equals to pi times 30 over 4 over 2. 30 over 4 over 2 is 30 over 4 times 2. So the area of the green semicircle equals to, here we have 30 over 2 is 15. So in total this expression equals to 15 pi over 4. 15 over 4 is 3.75. So in total this expression equals to 3.75 pi. And 3.75 pi equals to 11.78 square meters. So in conclusion, I shall find out that according to the second method also, the area of the green semicircle equals to either 3.75 pi square units, so in terms of numbers it equals to 11.78 square units. Okay, so finish with the second method. In the next step, I will summarize the lecture. We start with the first method. In this lecture, we found out the area of this green semicircle using two different methods. In the first method, we know, in addition, that this is 9 7 AC equals to 5 units in its length. 9 7 AC equals to 5 units in its length. 9 7 CB, this is 9 7 CB, this equals to 1 unit in its length. Again, our mission is to find out the area of this green semicircle. So in the first method, we joined points P and B together by straight line. And then I copied the white semicircle in a new page and implemented all 7 in the white semicircle. This is the white semicircle that I copied from the original drawing. AB is of course the diameter of this semicircle. by joining points P and B together by straight line, we get the peripheral angle APB. Peripheral angle APB is subtended on AB, that is the diameter of the semicircle, and therefore, according to rule 7, peripheral angle APB must be equal to 90 degrees in its size. Likewise, we join points P and C together by straight line. Then I copy the green semicircle in a new page and we implemented rule 7 on the green semicircle. This is the green semicircle that I got from the original drawing. Actually, by joining, first of all, AP is of course the diameter of the green semicircle. Here AP is the diameter of the green semicircle. By joining points P and C together by straight line, we get the peripheral angle ACP. This peripheral angle ACP is subtended on AP, that is the diameter of this green semicircle. Therefore, according to rule 7, peripheral angle ACP must be equal to 90 degrees in its size. If you focus on the original drawing, from this original drawing, it is very easy to see. This is angle A, that is a common angle. It belongs to both the green triangle APC, and angle A also belongs to triangle APB. Therefore, angle A is a common angle that belongs to both triangles. So we define the common angle A as alpha. So here, this is the common angle A, and it is equal to alpha according to our definition. So in the right triangle APB, this angle equals to alpha, this angle equals to 90 degrees. Therefore, this third missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. Likewise, in the main triangle APC, this is angle A that is equal to alpha according to our definition. This angle equals to 90 degrees actually according to rule 7. And therefore, this third missing angle must be equal to 90 degrees minus alpha. In the next step, we proved that this white triangle APB is similar to this green triangle, triangle APC. So I copied the two white triangles in the new page and we proved that the two white triangles are similar to each other according to angle similarity rule. So actually, those are the two right triangles that are going from the original drawing. Why those two right triangles are similar to each other? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. In addition, this is angle alpha, that is the common angle, and it belongs to both triangles, so we can write down that the angle alpha equals to itself is the common angle that belongs to both triangles. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So I should prove that all the triangles of this green triangle APC are correspondingly equal to all the triangles of this white triangle APB. Therefore, those two right triangles are similar to each other according to angle similarity rule. Repeat again. We actually prove that the white triangle APB is similar to the green triangle APC according to angle similarity rule. And from the fact that the two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that side AB in the white triangle over side AP in the green triangle equals to side AP in the white triangle over side AC in the green triangle. Again, we derive that AB over AP equals to AP over AC. AB is 5 plus 1, that is 6, and AC is 5. Again, AB is 6 and AC is 5. Therefore, this equation, after we substitute AB by 6 and AC by 5, we get that this equation equals to 6 over AP equals to AP over 5. Here we cross multiply this equation, and I found out that 5 times 6 equals to AP times AP, that is AP squared. 5 times 6 is 30, so 30 equals to AP squared. We took out of this equation, and I found out that the missing sign AP equals to the square root of 30 units in its length. This is the missing sign AP, that is equals to square root of 30 units in its length. AP is the diameter of this green semicircle, and it is equals to the square root of 30 units in its length, and therefore the radius must be equal to half of it. The radius R equals to AP over 2. Again, the radius R must be equal to the diameter AP over 2. AP is equal to 30, and therefore the radius R must be equal to the square root of 30 over 2. Again, the radius of this green semicircle equals to the square root of 30 over 2. Our mission is to find out the area of this green semicircle. The area of this green semicircle the area of this green semicircle equals to pi r square over 2. Repeat again. The area of this green semicircle equals to pi r square over 2. So it is pi, r is equal to 30 over 2, therefore r square is equal to 30 over 2 square divided by 2. So the area of the green semicircle equals to pi times r square. So we open the brackets here. Square root of 30 square is 30. Over 2 square is 4 divided by 2. So there the green semicircle equals to pi times 30 over 4 over 2. 30 over 4 over 2 is 30 over 4 times 2. So in total this expression equals to 30 pi over 4 times 2. Here we have 30 over 2 is 15. So in total this expression equals to 15 pi over 4. And here 15 over 4 is 3.75. In total this expression, therefore, in total, this expression equals to 3.75 pi, and 3.75 pi equals to 11.78 square units. So in conclusion, we found out that according to the first method, the area of this green semicircle equals to either 3.75 pi square units, or in terms of numbers, it is equals to 11.78 square units. We finished with the first method. In the next step, I presented to you how to find out the area of this green semicircle according to the second method. In the second method, we join points P and B together by a straight line, and then I copied the white semicircle in a new page, and we implemented again all 7 on the white semicircle exactly as we did in the first method. So this is the white semicircle that I got from the original drawing. By joining points P and B together by a straight line, we get the peripheral angle APB. AB is of course the diameter of this white semicircle, and we have peripheral angle APB that is subtended on AB, that is the diameter of this white semicircle. Therefore, peripheral angle APB must be equal to 90 degrees in its size according to rule 7. You can see here that peripheral angle APB equals to 90 degrees in its size according to rule 7. So we know that peripheral angle APB equals to 90 degrees. It means that line segment BP is perpendicular to PA. Again, this angle equals to 90 degrees. It means that line segment BP is perpendicular to PA. So here, line segment BP is perpendicular to PA. PA is the diameter of the green semicircle. Therefore, the center of this green semicircle must be located somewhere between points P and A, because PA is the diameter, and therefore the center must be located between points P and A. So this is the center of the green semicircle that we defined as O. So point O is the center of this green semicircle, point P is the point on the green semicircle itself, therefore PO is the radius of this green semicircle. Again, PO is the radius of this green semicircle. In conclusion, we found out that line segment BP is perpendicular to the radius PO of this green semicircle. Again, line segment BP is perpendicular to the radius PO of this green semicircle. And whenever you have a line segment that is perpendicular to a radius of a circle, you can implement rule 1. And quickly on rule 1. According to rule 1, a tangent to the circle is perpendicular to the radius drawn to its point of tendency. So in the domain we have a circle and we have the radius OM is equal to R. Line segment AB is perpendicular to the radius MO, and therefore line segment AB is defined as a tangent. Again, because of the fact that line segment AB is perpendicular to the radius MO, line segment AB is defined as a tangent to this circle. Actually, you can see that line segment AB is tangent to this circle point M. So whenever you have a line segment that is perpendicular to the radius, then the line segment will be defined as a tangent. So we can implement rule 1 in our drawing. Why? Because in our drawing we have here line segment BP that is perpendicular to the radius PO, and according to rule 1, line segment BP must be defined as a tangent to the green semicircle. Again, because of the fact that line segment BP is perpendicular to the radius PO of this green semicircle, line segment BP must be defined as a tangent to this green semicircle. Okay, so you can see here that line segment BP is a tangent to the green semicircle at point P. In addition, from the same common external point, so from point B we have tangent BP to this green semicircle. In addition, from the same common external point B, we have here chord CA. And therefore we can implement here rule 10. I'll click quickly on rule 10. Rule 10 is true in any circle, so in any circle, if AB is a chord in the circle and PT is a tangent to the circle, then the following equation is true, that PT squared equals to PA times PB. Again, PT squared equals to PA times PB. So from the common external point P, we have tangent PT, and from the same common external point P, we have here chord AB. So we can definitely implement rule 10 in our drawing. Why? Because in our drawing, if we focus on this common external point B, from this common external point B, we have tangent BP to the green semicircle, and we also have here, from the same common external point B, chord AC. So all the requirements of rule 10 are satisfied, and therefore we can implement here rule 10. According to rule 10, BP squared equals to BC times BA. Again, BP squared equals to BC times BA. And again, according to rule 10, BP squared, PB squared doesn't matter, equals to BC times BA. Okay, so PB is the missing tangent, so we write as it is. PB squared equals to BC. BC is 1, so substitute BC by 1, times AB. AB is 5 plus 1, that is 6, so substitute AB by 6. So in total, actually found out that PB squared equals to 1 times 6, that is 6. So PB squared equals to 6. We took a root out of this equation and found out that the missing tangent PB equals to the square root of 6 units in its length. This is the missing tangent PB that equals to the square root of 6 units in its length. In the next step, I copied the right triangle APB in a new page and implemented the Pythagoras theorem in this right triangle APB in order to find out the missing side AP, because we know that PB equals to the square root of 6 units in its length and AB equals to 6. The only missing side is side AP. So actually, this is the right triangle APB that I come from the original drawing, and repeat again that PB equals to the square root of 6, and the hypotenuse AB is 6. So according to the Pythagoras theorem, in a right triangle, the square of the hypotenuse equals to the sum of the sides of the perpendiculars. The hypotenuse in this right triangle APB is AB, therefore the square of the hypotenuse is AB square, and it must be equal to AP square plus BP square. AB is 6, therefore AB square is 6 squared, that is 36, and it is equal to AP square. AP is the missing side, so we leave it as it is, plus PB square. PB is square root of 6, therefore PB square is square root of 6 squared. Square root of 6 square is 6. So in conclusion, we should find out that 36 equals to AP square plus 6. We subtract 6 from this equation, and finally found out that AP square equals to 36 from 6 is 30. So AP square equals to 30. We took out of this equation, and finally found out that the missing side AP equals to the square root of 30 units in itself. This is the missing side AP, that is equals to the square root of 30 units in itself. AP is the diameter of this green semicircle. If AP is the diameter, it means that AP over 2 is the radius. So the radius R of the green semicircle equals to AP, the diameter AP over 2. AP is equal to 30, therefore AP over 2 is equal to 30 over 2. In conclusion, we should find out that the radius of this green semicircle R equals to the square root of 30 over 2. Again, our mission is to find out the area of this green semicircle. The area of the green semicircle, of course, equals to pi r square over 2. Repeat again. The area of the green semicircle equals to pi r square over 2. So it is pi r is equal to 30 over 2, therefore r square is equal to 30 over 2 square divided by 2. So it is pi, here open the bracket, square root of 30 square is 30, over 2 square is 4, divided by 2. So the area of the green semicircle in total equals to pi times 30 over 4 over 2 is 30 over 4 times 2. So in total the area of the green semicircle equals to 30 pi over 4 times 2. 30 over 2 is 15, so in total this expression equals to 15 pi over 4. 15 over 4 is 3.75, therefore in total this expression equals to 3.75 pi, and 3.75 pi equals to 11.78. So in conclusion, in both methods, we found out that the area of this green semicircle equals to either 3.75 pi square units, or in terms of numbers, it is equal to 11.78 square units. Okay, thank you very much.